Hello, my name is Raf Byrne, creator of Universal Turn-Based AI, and the purpose of this video is to give you an overview of the Universal Turn-Based AI system and go through some examples and show you how easy it is to get started with it and how you can apply it to your own turn-based game projects in Unity. So we're going to get started with an overview of the Universal Turn-Based AI system. Now I'm just going to open the documentation, which you can get here at eternalgoldenbraid.com. It's my website. Now we're just going to look at this diagram, and it sort of shows how all the different pieces fit together. So this here is the turn engine. It uses an implementation of the minimax algorithm, and it employs as well the alpha-beta pruning improvement to that algorithm. I'll go through that algorithm in a little bit for those people who maybe aren't familiar with that algorithm. It'll help you maybe understand a little bit more about the system and how you should be using it. So that's all sort of set. You just plug your bits into the engine. And everything here in the domain knowledge box, that's all of the information, that's where you encode information specific to your game. And there's three main parts that you have to provide the turn engine, and that is game state, turn, and an evaluator. And in the system there's three interfaces for that: game state, turn, and evaluator. And they provide method signatures for the methods required for the turn engine to work, and we'll go through those a little bit later as well. So a game state is some internal representation of your game. It's not like the game objects that you're going to use to represent them, the actual like physical or visual parts. It's more abstract descriptions of positions on the board for like a board game, or resource counts, whether like if you've got buildings built, positions of units, that kind of thing. But again, in an abstract way. It doesn't have to be the literal game objects themselves. You have to have a turn, which is a description of all of the actions a player can make in a single turn, and how those actions can be applied to a game state to turn it into the result of that turn occurring. For example, in chess, it would be moving a single piece. In Go, it would be putting one stone onto the board. Or in a more complicated turn-based game, say maybe Civilization or something like that, it would be, all of the movements of each individual troop, any building improvements that you can build in any of your cities, any worker improvement stuff, all of that summed up together would be a single turn. And the game state as well has to be able to provide a way that, given any particular game state, generate all of the possible turns of that game state. So any action that the current player, the player whose turn it is, any action they could make in that game state. And then we also have an evaluator here, which is a way to tell the system how much that game state is worth in terms of if it's better for the current player to win or lose in. So you would give the maximum value to a game state in which the current player wins, and you'd give the minimum value to the state in which the current player loses. And this is sort of where knowing a little bit about the minimax algorithm will be helpful. So it's just a picture of a tree, and all of these A, B, B1, B2, B3, whatever, these are all boards, right? These are all game states. So say the game is currently in state A, and then let's say it's a two-player game. It's currently in state A, and the player 1 can take action 1, 2, or 3, right? If they take action 1, they go to state B1. If they take action 2, they go to state B2. So the algorithm will generate these 3 turns from state A, apply them to state A, and get states B1, B2, B3. And then it'll search down to B1, and it'll say, and then it'll swap turns. So as a part of applying this turn, it has become the other player's turn. So we'll say, then the opposing player, say player 2, can take action 1, 2, or 3, and generate states C1, C2, C3, where it's now player 1's turn again. And if they take those, then if they take those, we get these states, and these states have values for it. So player 1 takes this action, the state has value 2. If they take this action, it has value 5. And basically, if it's our turn, like in this layer where it's player 1's turn, the system will select the action that has the highest value. So here it'd select 11, here it'd select 8, here it'd select 10, and then these states will get that value. But now going back up to B1, now that these states have values 5, 11, and 8, because it's playing from the opposing player's point of view, it selects the minimum, hence the name minimax. It'll select the minimum value between those states, which of these would be now 5. So even though down here there's a state in which we can get 11, really we can only maximally get 5 because the opposing player will never, like, it is optimal for him to force us into a state where we can only get the minimum, that value of 5. And then it'll go back up, and then of these, it'll figure out, based in the same way, which of B1, B2, and B3 is the best for player 1 to take from state A. So that's why we have this evaluator, because we can't, this state space might be very large, much larger than this, and in a reasonable amount of time, you wouldn't be able to search the entire tree. So we have this evaluator that lets us assign value to non-terminal states. So we can assume here that the system has only just searched up to depth 4, right, or 3, or depending on how you count it. So it's providing these values here, which are estimations of how much value that state could have in the future. And the further down the tree you search, the more accurate that value becomes. So if you know, some of these might end up at C6, where it's like there's a losing state here. Didn't have to search that far. You can just get win or lose. So that's what your evaluation function does. If it's a win or a lose or a draw, it'll return like max, the median value, the minimum, the average value, the max value, the in-between value, or the minimum value. And for other states where it's just these, we call them leaves on the tree. For those leaf states, it'll return an estimation. So, for example, in like a simple chess evaluator would maybe count the pieces for both sides and give them different values based on the piece type. Like, you know, you give kings more value, and that would be a very simple, naive check, because that doesn't look at where those pieces are positioned. It doesn't look at if those pieces are blocked, how many moves those pieces had. But it gives an estimation of how well a particular player is doing. and they're always written from the point of view of a particular player. So we'll continue with the chess example. The white player's AI would always evaluate states from like at the root level from the white player's perspective. It doesn't swap evaluation functions when it's thinking as the other player. Your evaluator has to be symmetric. So anything that is good for the white player is bad for the black player, and vice versa. Yes. And so if you implement all those three things, plug them into the turn engine, and you just request turns, and then it spits turns back out at you. So we'll go through an example. This is just a blank Unity project with the universal turn-based AI package imported into it. We've got two examples, Connect K and Tic-Tac-Toe. I'm just going to go through the Tic-Tac-Toe example this time because the Connect K example is quite a bit longer, and the Tic-Tac-Toe example is pretty simple. Yeah. So here are the three things we had to implement: Tic-Tac-Toe, Tic-Tac-Toe board, Tic-Tac-Toe turn, Tic-Tac-Toe evaluator. And those implement, as we can see, iGameState, iTurn, and iEvaluator individually. Looking at those interfaces, we can see that game states just have to have a check to see if the state is terminal. That indicates that a win or a loss or a draw. Basically, it's any state where you can't make any more moves. It has a coroutine for generating turns and a clone function to generate another copy of this game state with new references. And it's very important that when you write your clone functions, that if you have any reference type fields in your classes, that you have to copy all of those, make new instances of them, because otherwise your turn code, your turn application code will overwrite those from an old class. So in our example here, if we take this A state, if we don't make a copy of A when we apply the turn and make the B1 state, we'll overwrite A and make A into B1. So now we don't have A up here anymore, we've got B1. And we go to make B2, we're making B2 out of B1, and it won't be B2, it'll be, C1, assuming these turns work the same way. So that's why we have to have the clone method. Alternatively, you can just do the checks in the turn, but the system does the cloning anyway. So it's just to make sure. This has to be a coroutine, and that's just because it allows us to do lazy evaluation of the states. So, whoops. Again, in our example here, if we do some pruning, it comes into instance when we do alpha beta pruning, but basically, without going into too much detail, we can get rid of some states, some branches of the tree, if we know that we can't do any better anymore, because it's always going to go a particular way. And if that's the case, if we can do the pruning, then we don't have to generate these turns, we don't have to generate these states. But if it wasn't a coroutine, then the only other way you would do it would be to generate all of the states, put them in a list, and then iterate through the list. And this way we can only generate the turns as we need them. iTurn doesn't have much requirements, just a function to apply the actual turn. And iEvaluator has to have a min value, has to have a max value, and some evaluation of the value of the state. So, in our tic-tac-toe example, this is our game state, TTT board. It's very simply a list an array of TTT piece here, which is either empty, X, or an O. We set it to length 9 because there's 9 positions on the board. Yeah, we do some initialization. Is terminal function checks if anyone has 3 in a row, and then it checks if the board's full. So if anyone has 3 in a row, then one person has 1. If the board's full, then it's a draw. That's how we know if it's terminal. And these functions are used by the evaluator, winner and loser. Here, and then you can see down here the generate possible turns. We iterate through each position. If there's nothing there, then we can put a piece in that position. And this is how you set up in case you're unfamiliar, this is really the only difference for setting up a coroutine like this. It's just whenever you would maybe add the turn to a list or return the turn, you just do a yield return. It's that easy. And then here the clone just calls our clone constructor that makes it another board from an old board. So it makes a new array and copies in the values. And that's what I was talking about if you have things of reference type. Our TTT turn is just, this X is just the position in that array of TTT board of where to put the piece and what kind of piece we're putting down. And then evaluator just returns its max value if the evaluator's player wins, and its min value if they lose, and otherwise 0. And the reason that in this example that we don't bother doing evaluating state non-winning or losing states is because the search tree for tic-tac-toe is just very small. The amount of time taken to search that tree is milliseconds or less. So we just assume that we're always going to be able to search the entire tree. So we'll always be able to see whether or not taking this path will win or lose. And then the other thing in this example is the game controller, tic-tac-toe. So this is our sort of controlling class. This is mono behavior. This is going to exist in the scene, and this sets up the two AIs to play against each other. And we'll see how we do that. So we have two turn engines here, the XAI and the OAI. And this is how you initialize them. There's two different turn engines. There's the single-threaded turn engine and the multi-threaded turn engine. There's no difference in the way that they will produce turns, but one does everything in a single thread. The other one spawns multiple threads per initial branch of the tree. So in that example before, for the B1, B2, and B3 trees, those would all be running in separate threads. That it's not always, the multi-threaded one isn't necessarily faster because of the overhead of managing multiple threads. So don't be surprised if you try the multi-threaded one and it just doesn't perform as well. It's really only if in that initial tree, if you didn't have B1, B2 through 3, you had B1 through thousands, hundreds of thousands. If that level of turns, initial turns, you're going to see performance improvements from the multi-threaded one. Otherwise, you're not really going to. But I've included it anyway, in case you make that type of game. So yeah, these take... There's a couple of different constructors that I can show you. This first one, you take the evaluator, you take the depth limit, and whether or not we're going to collect stats. Now, the evaluator, remember, is that the evaluator for the AI from their perspective. So you see, for the OAI, we make a new TTT evaluator, and that's evaluating from the perspective of the O player, and for the X, from the perspective of the X player. yeah, and then that's just the way you set it up. Depth limit here, there's only 9 possible turns, there's only 9 positions on the board, so we just search to 10, because why not? And we just always search the entire tree. You can also instead set a time limit, or you can set both. If you set the time limit, if you set just a time limit, it'll search as far as it can in the amount of time in seconds that you give it. And that's really useful when, unlike in tic-tac-toe, the search tree is much, much larger. Say, for example, chess. There's many more moves. Some branches have, it kind of goes infinitely, or almost infinitely. It's quite large. This space is too large to search everywhere. So we set a time limit. The system will search as far as it can in that time, and then return the best value it found so far. And that's the main way you're probably going to use it, unless you're doing very simple games like tic-tac-toe. Otherwise, you can set a depth limit anyway, so it'll search either up until that depth or to the time limit, whichever happens first. And that's just because if you know the bound for the number of, so the depth limit here is like the number of moves you want to look ahead. If you know that there's only ever going to be, for example, in tic-tac-toe, 9 moves, or in our Connect K example, there's only as many moves as there are positions on the board. Setting a time limit and a depth limit means that it can end early. If you set only a time limit, it'll always search up until that time, and it'll just it'll sort of search past the end of the board. But if you set a time limit and a depth limit, it can sort of end early when it reaches the depth limit instead, which is useful if you want to have an AI that searches. It'll search it'll use up all the time if it needs to, but otherwise it'll try and end early. So when you want to request a turn, you call start coroutine. So this is get next turn for a turn engine is a coroutine. You pass in the starting state, the current state of the board, and and it'll sort of work. And then when it's found the turn, or when its time limit is reached, or when its depth limit is reached, the turn engine will call this event called the turn ready event, and it'll call whatever function you set to receive turns. So in this example, we just use one function called receive turn that gets in the new board, and the delegates, the functions for the events always have this signature void, return type void, and they take a single parameter, which is an I turn, which is the best turn that the engine found. And in this example, we use just the single function, and we do the turn flipping. You could use, if you wanted to, you could use different functions to receive turns that would tell you whose turn you're receiving and stuff like that. And this sort of call and call back method lets you do stuff, pretty asynchronously. You don't have to keep looping through and checking if the turn's ready or anything. It'll just tell you when it's ready. And all your UI and all your animations, everything's going to keep going. Your game controller doesn't have to pause and wait for the turn to come back, which is very useful. So to get a new turn, you call start coroutine, your turn engine, get next turn, and to receive a turn, you register for the turn ready event like this, and then do the work of receiving the turn inside that function. So that pretty much covers the tic-tac-toe example. You can see it going here. It's only going this slow, because we're sort of artificially slowing it down, so we can set this down to really to 0. And you can see that it's just going to keep going, and it's going to draw forever because it always knows the optimal move to make in every situation. So, I hope this has given you an overview of how tic-tac-toe, how universal turn-based AI, can help you make turn-based games. There's another example included in the project, Connect K. It's a little bit more involved. The board is a little bit more complicated. The evaluator is a bit more complicated, and we use this class called Turn Agent that just sort of it makes a generic interface for a human player and for an AI player, so that it can receive turns in the same event capturing way. And that was just a sort of convenience. You don't have to do it that way. Obviously, it's a very flexible system, so you can, this is one way we've done it where everything's happening in the controller, and in the Connect K one there's a game controller and then individual mono behaviors for different players, and that's totally fine too. So I hope that you can continue to use universal turn-based AI in the future.